Today we are going to start topic 3, plate tectonics, and we're going to begin with lesson 1 on page 98 of your textbook, which is evidence of plate motions. Okay, we're going to start the connect it on page 98, and it wants us to draw lines between South America and Africa to show how the contours of each of the two continents would fit together. And so it's going to look something like this. In your textbook, it's a little bit different because you have the Earth model in there, and it's a little bit easier, but your arrows should look something like this on your Earth. And then what might you infer about South America and Africa if you thought the continents, were movable objects? And it looks like they could maybe be stuck together. So that would be the answer that we want for that, is that they'd once been stuck together. All right, so the hypothesis of continental drift. In 1912, Alfred Wegener, a German meteorologist, developed the hypothesis that all of the continents had once been fused together and then drifted apart. It became known as the theory of continental drift. Wegener gathered evidence to support his hypothesis that a supercontinent, called Pangaea, had broken up into the continents we know today. A hypothesis is an idea that can be tested by experimentation or investigation. Evidence from land features. Wegener found other evidence to support his continental drift hypothesis. Evidence that mountain ranges on different continents line up because they were once connected. Coal deposits made from warm weather plants were found in regions that no longer support that kind of plant life. Here is a link to the continental drift video. You can get to that link in the PowerPoint instead of the recorded notes, or I will post it in Google Classroom as a material or resource. Evidence from fossils. Fossils of Glossopteris, a fern-like plant from 250 million years ago, were found on 5 continents, suggesting that those landforms had once been connected as part of Pangaea. And fossils of Mesosaurus, which was a reptile that lived in freshwater habitats millions of years ago, were found in both South America and Africa. So this image here is similar to our figure 2, where you are asked in your textbook to study the map key to see how Wegener pieced together similar pieces of evidence from separate sites to support his hypothesis. So present-day India is in South Asia at the northern end of the Indian Ocean. What evidence found in India matches that of other locations? So the Lystrosaurus from our key is there. The Glossopteris plant is also there. And fossils were found in India, Africa, as well as Antarctica that were all similar. So that should be your answer to interpreting visuals. Evidence from climate. So Wegener, as we know, he was a meteorologist, gathered evidence to show that Earth's continents had experienced different climates than the ones they have today. An example, Spitsbergen, an island in the Arctic Ocean, has fossils of plants that could have survived only in a tropical climate. Spitsbergen used to be near the equator as part of Pangaea. So, what is the general pattern in the evidence that supports the hypothesis of continental drift? Things found at multiple sites. Okay, sorry about that. Mid-ocean ridges. Wegener's continental drift hypothesis contained lots of scientific evidence, but couldn't explain how the continents broke apart and moved, so it was rejected. Later, oceanography and undersea exploration renewed interest in continental drift and provided evidence that Earth's surface was comprised of moving plates, large pieces of the lithosphere. Scientists measured the distance from the sea surface to its floor and discovered 70,000 kilometers of mid-ocean ridges, which are long zipper-like chains of undersea mountains, like the Mid-Atlantic Ridge. So we're going to use this image here, which is similar to Figure 3, which is a mapping of mid-ocean ridges in the mid-20th century, provided support evidence that Earth's surface was composed of moving plates. We're going to do the interpret visuals. Do any of the mid-ocean ridges appear to extend into continents? Which ones? So over here in our textbook, we can see the East Pacific Rise right here. Appears to run into the west coast of North America, which is right around where California is. All right, seafloor spreading. By gathering rock samples, geologists learned that mid-ocean ridges were the source of new spans of the ocean floor. Seafloor spreading is molten rock flows up through a crack in Earth's crust and hardens into solid strips of new rock on both sides of the crack. Then the entire floor on either side of the ridge moves away when new is made. So the older strips move away from the ridge and the newest is at the ridge. So this is Figure 4 in the textbook. And we have obviously this isn't exactly the same, but it's very similar. So we have the oceanic crust labeled at the top, and we have our, right here, in this general area is the mid-ocean ridge, right, which is labeled here. And then we have molten material, that is in this area. So that's where our molten material is, and you should label that. And now we're going to go ahead and do the reading check. So why was undersea exploration important for developing the theory of plate tectonics? And it revealed mid-ocean ridges where new crust is made. Ocean trenches. Subduction is the sinking movement of the ocean floor, which occur at ocean trenches. Ocean trenches are undersea valleys that are the deepest part of the ocean. Cooler, denser slabs of oceanic crust will sink under the edge of a younger, less dense slab of oceanic crust. This can produce volcanic eruptions. If oceanic crust meets continental crust, then a chain of volcanoes will form. If it meets more oceanic crust, then a chain of volcanic islands will form. All right, so Figure 5 of your text is subduction, and oceanic plates, which form from seafloor spreading, sink back into the mantle at subduction zones. So we're going to label the mantle, mid-ocean ridge, and ocean trench. So the mantle, of course, is going to be right here, M-A-N-T-L-E. It is very hard to write on here. All right, next we have the mid-ocean ridge, and that's going to be in the middle here. So we're going to write mid. I'm not going to write it all out. If you guys will, I would appreciate that. It's just very difficult to do so on here. So this is the mid-ocean ridge, which means that this over here is going to be our ocean trench. And you guys should make sure to write that out and label it in your workbook. All right, so subduction and the oceans. So an ocean basin can have a spreading ridge, subduction zones, or both depending on its age. The Atlantic Ocean has the mid-Atlantic ridge running its full length, but no subduction zones. The Pacific Ocean is older and is surrounded by subduction zones. Its oceanic crust is being recycled back into the mantle faster than it is being created. So the Pacific Basin is getting the Pacific Basin is getting smaller. Eventually will be where a new supercontinent could appear. All right, so here we have our model it, but before we start that, let's do our reading check. What features are evidence of the Pacific Ocean's maturity? And the answer to that would be subduction zones on many sides. So our model it figure 6 is predict North America's movement. The map shows the layout of some of Earth's land masses, the mid-ocean ridges where plates are made, and ocean trenches where plates are recycled. Draw a line to indicate where you think the west coast of North America will eventually be located. And we're going to draw a line right around here. Should look something like that. That would be over the plates. All right, so now it is time to do our lesson check. So 1, describe the hypothesis of continental drift. So millions of years ago, there was a single landmass called Pangaea. Over time, it broke into continents that drifted slowly into the positions we see them in now. 2, how did the study of fossils provide support for the ideas behind the existence of Pangaea? Finding the same types of fossils on different continents, especially fossils of organisms that couldn't swim across oceans, suggested that the separate continents had once been together. Fossils of tropical plant species in polar areas also suggested that the continents had moved from the equator to the poles. 3. How did the discovery of mid-ocean ridges support the hypothesis of continental drift? It provided an explanation of how Earth continually generates its crust. 4. A large oceanic crust collides with the edge of a continent. What will happen? The oceanic crust will subduct under the continental crust and be recycled back into the mantle. 5. A remotely operated vehicle is sent to the deepest part of the Mariana Trench. It returns with a sample of rock from the ocean floor. Would this rock be old or young? Explain. So this rock would be very old. If it's ocean floor at the deepest part of the deep ocean trench, then it's oceanic crust that was made millions of years ago at a mid-ocean ridge that may be far away. And that is the end of topic 3, lesson 1.